Welcome back to the course on audio signal processing for music applications. This week, we're talking about the application of audio analysis in the description of sounds. In the last lecture, we talked about audio features, presenting various spectral-based analysis methods with which we can obtain features of a sound that might be relevant for describing it. Now, in this lecture, we want to go beyond the idea of describing single sounds and introduce the concept of describing collections of sounds. So we'll first present the idea of the music information plane, and then we will distinguish between sounds and music with the aim of developing methodologies that are either relevant to the more generic concept of sound or more specific for the characteristics of music. So we'll first talk about sounds and sound recordings, and then collections of sound recordings. And then we'll continue with the idea of music recordings and collections of music recordings. So this is the music information plane that should help us understand what do we mean by music description in our particular context. So we consider different abstraction levels, and the left column are these different abstraction levels, and we can go from the physical level, which is basically the lowest level that we are dealing with, and we go up to the cognitive level. Okay, so that would be the highest level that we consider, and some steps in between. So at the physical level, when we talk about sounds and music, we can talk about concepts like the frequency or the duration of the sound, or the spectrum and some clear characteristics of the spectrum like the centroid, and also we can talk about intensity of the sound. If you go a level higher, the sensorial level, then instead of frequency, we can talk about the pitch of the sound. And then in terms of duration, we can talk about time, so the sensorial time of the duration. And then instead of talking about spectrum, we can talk about timbre, which is a sensorial concept. And finally, in terms of intensity, now we talk about loudness, which again is a sensorial concept. And we can go a level higher and talk about perceptual topics or perceptual concepts that are more musical, that are related to musical concepts. So in here we talk about successive and simultaneous intervals of pitches, what will be called notes. And then when we talk about time, we talk about the structuring of time, and we talk about things like the beat. And then the timbre, we talk about aspects of the timbre that we can identify and characterize with some aspect of a musical sound. And for example, the spectral envelope would be that. And then finally, instead of loudness, when we talk about musical loudness, we normally refer to dynamics, and we have a vocabulary that talks about the dynamics of musical sounds. And we can still go a level higher and go towards the more formalized way of talking about musical concepts. And therefore, when we talk about pitch-related concepts, we talk about things like melody or key or tonality. When we talk about timing-related concepts, we talk about rhythmic patterns, we talk about tempo, we talk about meter. And when we talk about spectral timbre characteristics, we identify musical instruments or the voice as entities that have a characteristic timbre. And then finally, when we talk about dynamics or loudness, we are interested in the articulations of the sounds and how sounds change from one to another. And finally, we can reach the highest level, the cognitive level, the level that relates to as humans in a very subjective way, and how we listen to music, and what issues are relevant for us in the interaction with music. So at this level, the columns are not anymore valid. There is interaction between all these different concepts, and then we can talk about the emotion or the musical style or semantic concepts that clearly integrate all these other levels of descriptions to obtain these concepts, these ways of describing music that are clearly more generic and definitely are subjective or cultural, and that would be a level that definitely would be hard to reach, and in this class we are definitely not going to talk much about that. So we will focus on the low-level descriptions of sounds, hopefully reaching a high enough level of description that is of relevance to user applications. If we want to describe sounds in a generic way, sounds like the ones we find in Freesound, we can group audio features, the audio features that we talked about in the last lecture, and we can group them in different categories. So we can talk about the timbre related features, and we mentioned quite a few of them, like the spectral centroid or MFCCs or the high frequency content, etc. Then we can talk about another group of features that relate with dynamics, and that's basically the loudness and the level of a particular recording. Then we can talk about the pitch related features, and here is where we can talk about the pitch or the pitch salience. And finally, we have to describe also the time varying aspects of it, aspects of a sound that relate to the evolution of the sound, to the texture of the sound, and these we can group them under the term morphological features. And here we can talk about things like the envelope of a sound or the onset rate or many other type of descriptions that we could include under this. We already have seen quite a few of these descriptors. So what is interesting now is from these descriptors, from these features that we can analyze, we can now talk about collections of sounds. So let's talk about how to describe collections of sounds. And clearly there are many ways that we can analyze a collection of sounds and describe it. And we'll focus on three basic concepts. The first one, and the most important concept that we need to develop, is the idea of similarity. If we want to talk about a collection of sounds, we have to talk about the similarity between the sounds, so we can form the idea of collections and group them. Once we can talk about similarity, then we can cluster sounds. We can group sounds according to some criteria. And finally, if we know some classes, some existing labels that we use to describe a particular group of sounds, then we can classify sounds. We can assign classes to particular sounds. In our context, sound collection can be represented by a diagram like this one. We consider a sound as a set of audio features, each feature having a numerical value. In order to properly describe a sound, we have to use many features, but for simplicity, we will be taking only, in this case, two features. So if we consider a sound as represented by two features, we can display a sound as a point in a two-dimensional space. And that's what we're seeing here. Every feature is one dimension. So here we are showing two audio features. The horizontal line is the mean of the spectral centroid. So we have analyzed notes of three instruments, of violin, flute, and trumpet. We have computed the spectral centroid and we have taken the mean of it. So this is a multi-frame feature. And also we have done the mean of one of the MFCC coefficients, the second coefficient. So that's the mean of the second coefficient in the vertical line. And we can see that the violin has a quite high value for this coefficient, for the MFCC value. and it has a centroid that covers quite a bit of space. The trumpet has this MFCC coefficient quite lower, so these blue dots are more in the lower side, and the flute sound is kind of an in-between, and also the MFCCs are in between, so that we can kind of see that these types of sound are distinct according to these two features. Now, in order to play around with this space, the most fundamental thing is to measure the distance between sounds, between points. So we have to find a way to, in a multidimensional space, not just in this simple 2D space, how we compared two sounds, how do we find the similarity between the two. So Euclidean distance is one of the simplest ways to measure the distance between 2 points in a multidimensional space. So in this case, P would correspond to one sound, the collection of features of one sound, and Q would correspond to another sound, the collection of feature values of the other sound. And then for every dimension, I, we just take the distance between those two values at that particular feature, then we square it and we sum over all the features, all the dimensions, and then we take the square root, and that's the Euclidean distance. In the case of a 2D space of just two features, that becomes much simpler. So in this case, the red and the blue are two sounds with two features, and we can just measure this Euclidean distance, and it's basically the line that that separates these 2 points, the length of this line. Now that we know how to measure distance, we can cluster sounds. K-means is a clustering algorithm, and if we give to the algorithm the desired number of clusters, it will create the clusters, and it will return the mean value of each of these clusters. K-means clustering aims to partition n observations, so the observations would correspond to the number of sounds, into k clusters, so into k categories or groups of sounds. And each observation belongs to the cluster that has the nearest mean. Okay, so this mean serves as the prototype of the cluster that we are creating. The problem of finding